Yeah, we're just waiting for others to join the meeting, and we're going to start the webinar very soon. If you have any question, feel free to include the question using the chat uh, part. And if you have a specific question, you can just raise up your hands. And at any point during the meeting, I'm going to stop to respond to your question. I just want to clarify, can you see my screen?
Yes, I
Oh,
see your
great.
screen.
Yeah, oh, great. So in the meeting, I'm going to be sharing on blasting assessment from mine to mill. So I'm going to be taking everyone in the meeting through how to assess your blasting, how to make continuous improvement based on the output of your assessment. And I'm going to show you how technology can be incorporated to assessing your blasting, and how you can also use technology to assess the material flow from the mine to mill. My name is Blessing Taiwo. I'm a technical specialist at Whipware. Whipware is a company that develop technology for material assessment, either after blasting or on the conveyor belt or on truck. We're based in Canada, Ontario. The company has been in existence since 1986. We are the pioneer of image analysis technology, and we are happy that our technology, including software and hardware, is thriving in mining industry. Currently at the ongoing Prague Blast conference, we have two of our paper with collaborated with other colleagues in mining industry being presented. One of the paper is presented on uh, setting up continuous improvement in granite quarry, where we showcase the application of the technology alongside with other mine technology to check your blasting and make continuous improvements on your blasting operation. This webinar is going to cover image analysis technology application, improvements and technology advancement from 1990s to 2024. Then I'm going to show a live demonstration of the software and the interface of the hardware to educate us on the current state of image analysis as at today. Application, what are those things that you can see as a focus when you want to assess your blasting? Blasting operation is not as easy as we think it is. You know, recently I have discussion with people, and the first question they always ask me is, why do we have variation in results? You might be working in the same bench, carrying out blasting in that same bench with the same parameter, and you have different outputs. You know, things, we have the rock condition not to be stable at every point in time. You can blast in this section of the mine today, and come tomorrow, the property of the material in that section will change, you know. Then if you choose to design the blast with the same parameter that you've done, that you used in the previous blast, then you might possibly be getting a different result. So some of the factors that affects the performance of our blasting, even in the same mine, on the same bench, includes the characteristics of the rock, like the strength of the rock, the discontinuity properties of the rock, and also the performance of the explosive during usage. So we want to put into consideration the status of the rock that we are blasting. If you keep using the same explosive energy with the same design, with rock condition varying every point in time, then you keep getting different results. So sometimes you might have issue like oversize, you might have issue like too much of fines. And when you have oversize, that is material bigger than your crusher, you definitely need to reblast the material. So why do you need to keep checking your blasting? You need to keep checking your blasting for reference and compliance sake. You want to reference the blast to the state of the mine, you know, the current state of the rock material that you are about to blast. You want to check the performance of your explosive, correlate this, and make sure you are complying with either safety or downstream operation desire of material. Also, you want to check your blasting to make sure that you control the quality. the material coming from the blast. You can't imagine you producing material that would give, the loader issue during loading operation, or that will not be able to go through the primary crusher. So the more you blast your material, the good the quality, the better the downstream operation will flow. Also, you want to check your blasting for oversize detection. You want to detect if you have material in that blast that is bigger than your desire, maybe bigger than the crusher or bigger than, the loader. Then you want to make sure that you have access to the quality of material that you are producing from this blast to aid your adjustment. You want to adjust the controllable parameter to fit into the current state of the rock. So these are some of the important. Also, sometimes you might be left with several decisions. Maybe you have 2 or 3 products. Maybe you have product from different mines, and you want from different explosive industries, and you want to compare the results from these different explosive material. It could be you want to compare 2 explosive, or you want to compare 2 detonation techniques. Maybe you want to compare electric detonator with non-electric detonator, or using amphor with your explosive as secondary explosive in that charge at the column step, or you want to incorporate another type of explosive. These are some of the reasons why you want to assess the performance of that blast, to compare product or to compare service. You can also make the decision to compare the state of the material in the mine to what the demand of the crusher is. So you want to ensure that this is well balanced, to make sure you don't have issue with your downstream operation. So here, image analysis technology are technology that allow you to carry out virtual sieve analysis. So just like sieving, where you take the material to the lab to pass through screen sizes. In this case, you are taking the picture of the material, you are assessing the material through virtual sieve. So the material being the picture of the material you captured is like you taking all those material in that picture, you run them through sieves. Then in this case, the sieve are virtual sieve, and up to 25 sieve sets. So you can easily adjust any of the sieve. And one of the advantage of this virtual sieving is that it allows you to, incorporate the size of your primary crusher, incorporate the size of other kind of parameter of importance. Maybe you want to see the number of the material in that blast that will be easily loaded by your excavator. Here is a case study of using image analysis to assess your blasting. Here, the first image here, you have the image A, is where the image analysis technology is used to assess the boulder. In the traditional approach, they call it boulder counting. You want to count the number of the particle in that blast that is bigger than your crusher. Definitely, if these materials are bigger than your crusher, you have 2 options, 3 options. It is either you separate the material away from what you are loading to the mill, or you use hydraulic breaker after the blasting, or you perform secondary blasting. Which all or any of these approach that you're using are capital intensive, and also safety is of concern. If you're going to be blasting boulder, some of us that you used to blasting boulder, it's difficult to blast boulder because there is high possibility of fly rock from a boulder. Since you have free face at every point in time, the boulder is in a free space, you can easily project any of the particle if you are trying to carry out secondary blasting. Then what about the cost of buying explosive to do the secondary blasting? So with image analysis software and technology, you can easily assess right on site which of the material that is coming out of your blast will not be compatible with your crusher. Then you can know where they are coming from. You know which part of the bench where these materials are located. So this information is useful to the loader, and it's also useful to you as a blaster man. You can easily incorporate this information with the next blasting. So if you keep getting a big boulder from a section of the mine, then you can pay attention to that section of the mine to improve the design. Sometimes if you have boulder at a particular section of the mine, you want to check the condition of the rock. You want to know if you might need to, adjust your burden and spacing. Image B is showing material characterization. With image analysis, you can also characterize your material. That is, put them in size classes. Based on the color on the screen, you can see the outer color are showing boulders. Boulders bigger than 90 percentage passing of that material. So the software or image analysis technology allow you to characterize this material. You can easily know those points where you are having issue. For example, on the screen right now, you can see most of the red dots, most of the red particles are located on the second bench, which is coming directly from the center of this blast. So it means most of the boulder is coming right from here. And if the boulder is coming from this area of this blast, the next thing to do is to ask ourselves the question, why am I getting the boulder from this section of the blast? Then the next thing is, if I need to change my burden or spacing, could it be that there is issue with the drill, or maybe there is deviation, or maybe there is discontinuity properties in this section of the blast? So what you can see from the results gives you the evidence to make changes, and confirmation of maybe you've been having the doubts that the center of this mine might have rock of different property that is affecting the performance of the blast. Then another thing that you can do with image analysis technology as a blaster man or as a mine operator is using the technology to assess the performance of your blast on site and correlate correlate each of the blasting on different benches. So here is an example of on-site tracking of blasting. You keep doing blasting on different benches, but you don't know how the design that you are using on different benches is affecting the fragmentation. With image analysis technology incorporated with GIX, on-site fragmentation tracking, you can easily know the zone on that bench that is affecting your fragmentation. Sometimes a single blowout O can affect the O fragmentation in a section of the bench. So if you keep getting blowouts on different bench at a single point, it's an evidence to let you know that probably you need to change the stemming condition, or you need to change the design at that zone. So here the image analysis technology is going to show you where you see red dots on the benches are places where the big boulders are coming from in that blast. So having known that the boulders are coming from those zones, you can pay attention to the next design by focusing on those areas, because the software is going to give you a 10 by 10 grid 10 by 10 meter grid section. As you can see, each of the boss is 10 meter by 10 meter, so you can easily know exactly that section. If you are using, for example, design of maybe 3 by 3 burden and spacing, then if you are getting boulder within 10 by 10 meter grid section of that bench, maybe it's a call to attention that maybe the burden at that section is not being compatible with the design. Then another thing that image analysis technology can help you to do is tracking different blasting. You can compare different blasting. For example, as you can see in image D, this is 3 different blasts in different benches in the mine. So as you move on the mine, you want to keep checking the performance of each of the blasts. Maybe your blast one, you use a specific design, and by the time you checkmate the design with image technology, which allows you to create an envelope. As you can see, the yellow envelope, you can create the yellow envelope as a specification for your client or as a specification for your mine. Some mines might tell you as a blaster man that the D80 or the D95 of your blast must be within so range. So for example, if the mine says, if you are giving us any material from the mine as a blaster man, we want 95% of that material should be smaller than 1000 millimeter. So if you are blasting to this specification, it means that 90% of the material you are blasting can easily go to the primary crusher. With this information, you can create this envelope to keep checkmating each of the blast. So when you perform the next blast, you have the information of the previous blast compared to the current blast, and these two blast or the three blast information can be compared to the expectation of the mill operator or to the expectation of the loader. Sometimes when we have a blast like in this case, when there is a blast like this, definitely loading this material will require some sorting. You need to do selective loading. So if the loader operator have this kind of chart or image, it can easily know where those big boulders that will be causing issue during the loading, because if the material is bigger than the bucket size, then you have the operator will need to do a lot of maneuvering before you can pick the material. This will delay the shift and we also delay the whole fleet operation. So you want to make sure you have this kind of information to make decisions using image analysis technology. How has this technology been? What is the status of the technology in the 1980s, in the beginning of image analysis technology application in blasting? The technology begins with the use of classic edge detection. This is an algorithm that allows blaster man to calculate or estimate the sizes of each of the rock and the blast using a combination of numbers to estimate the edges of the particles. So then there are two major issues with this algorithm in the beginning. The first issue is that there is a lot of disintegration. Disintegration in image analysis technology is when you have the technology detecting a single particle as multiple. So as you can see here, where I have my cursor, this is an example of the classic edge detection. This edge detection will require a manual editing, which can take longer time. So in this case, you need to find out those sections of this image after you've taken the picture and you've processed the image and the technology. You need to find out the section of the image that is having this integration issue. Then another issue is what is called the fusion issue. Fusion problem in image analysis technology is when you have the technology detecting multiple particles as one. So this will require a long time editing for the user. Then with the age of artificial intelligence as at now, the technology have improved in the place of using artificial intelligence to enhance the detection of the particle. So this is the same image processed by algorithm developed in the 1980s. Now this is the application of an advancement deep learning algorithm that allows the software to not only detect the particle but also correct for any effect of fusion or disintegration in the particle. So you can see a long a better improvement. So those people who are familiar with the old version of software like with frag 3, with frag 2, you see this kind of issue which will require you going to do the editing manually. So, but with the deep learning algorithm and AI incorporated into material analysis with image, you can easily correct for that. These are solutions available for image analysis either on the site after blasting or on the birds when you're transporting the material, or on the truck when you're loading or moving the material from the mine to stockpile or from stockpile to the crusher. The first technology we have here at Whipware is called the WhipFrag software, which I believe most of us are familiar with, and as shown in the previous image where I compare the old version of the software to the current state of the software allow user blasters to take the image of the material after the blasting either with their mobile phone, with digital camera, or with drone. So you can you can fly the drone after the blasting, then take multiple pictures at different sections of the blast. With the software, you can combine this image together to create a single auto photo, which you can easily analyze on the software. Then the second technology is call the Solo 6, which is a hardware kind of version of the software. But in this case, the hardware have a camera section that takes the picture automatically and analyze the picture uh, on a go. So this is an automated version of the software. So there is a camera on board that takes the picture of material on moving conveyor belts. As you can see, is denoted by the blue dots here. So it's taking the picture as the material is coming either from underground mine or from surface mine, either after primary crusher or after secondary crusher. So as the material is coming from the crusher, you want to see the particles of the material that is coming from the primary crusher before it goes into the secondary crusher. Why do you need this information? This information will enhance your decision making. Decision making about size reduction ratio, decision making about energy consumption of the crusher. If you are spending energy quality X to reduce this material from this state to this state, then you want to compare the percentage of reduction that the crusher have done on this material. So to have that in the early days, it always requires stopping the bet and taking a bet cut. But now with image analysis technology like Solo 6, you have the camera taking the picture 24/7 non-stop. Then you are getting the report on your mobile phone, which you can easily view using a WhoopFrag as a human machine interface. Then the Reflex 6, which is denoted by the red dot, is a hardware camera that you can install to take picture of material on the truck. So as the truck is tipping the material into the primary crusher, or as the LHD is loading the material from the draw point to the crusher inlet or to the screen, you have this camera taking the picture on the bucket. So it's taking the picture on the bucket continuously as the truck is tipping. It's taking continuous picture of different profile of the material and analyzing this in real time. Then you can have access to the chart. You can also use this system or any of the system, the reflex system or the Solo system, to control the crusher. Let's say in scenario where there are material coming from the mine, and the picture, you can have the reflex system not compulsory to be on the crusher upper. You can have it mounted between the stockpile and the crusher. So before it gets to the crusher, you take a picture of it, and based on the maximum size of material in the truck, you can easily adjust the inlet of the crusher to fit in the size of material. It's just like checkmating what is coming to the crusher before it gets to the crusher. Then this technology can communicate. It can speak to the crusher, checking the size of the inlet of the crusher and the size of material that is available. If the material that is coming to the crusher is having excessive boulders, material bigger than unusual size of material, then the system can check what the crusher can take, see if the crusher can be adjusted, increasing the inlet of the crusher to fit in instead of having crusher jam. These, among others, are what this system can do in real time. Now, how do you take the image? I'm going to start focusing on WeFrag software, and I also have my colleague here who will like to say one or two things about the online system when I'm done presenting on the WeFrag, where I'm going to be showing the interface of the software. You can, as I've mentioned earlier, you can take the picture with your mobile phone. This technology is compatible with your mobile phone, compatible with either Android or iOS device or iPad or whatsoever device you're using. The technology is compatible. Download the software and you can take the picture in the app. The advantage of taking the picture in the app is that you don't need to put a scale object on the mock pile. In the traditional days where there is a need for a scale on the mock pile, now with your mobile phone, you can take the picture in the app right there and do the analysis. You can also take the picture if you still want to abide with putting a scale object on the mock pile. You can take the picture with your camera, import the image from your camera into the software, and you can proceed with your analysis. Then you can also take the picture of the blast with a drone. Two advantage of taking the image with the blast image with drone. The first thing is that you will have access to the blast cap. the upper side of the blast that is blast material that is coming from the stemming zone. So the stemming zone is known to contain the inax material, which will definitely control the energy within that zone and below profile. So we have the stemming region, the column region of the blast, and the bottom charge. The column and the bottom charge they have explosive energy to distribute horizontally within the rock, but the stemming region only has inax material which control and confine the blast energy to be well distributed within the rock. So most of the boulders sometimes will be coming from the stemming region, forming the cap of the mock pile. So with the drone image, you can take a bird view image of this material and analyze them to assess your material coming from the stemming region. Then what happens if you have a very big blast and you don't want to use a drone, you want to take a picture with your mobile phone? Image analysis technology like WeFrag is advanced enough to allow you take multiple image. For example, if this is the whole of the blast, you can take one image here, another image here, then another image here, or as many image as you have. Then you can merge the three image or many image together to create a single analysis file. So the software is smart to give you a result for a single blast. If these images are coming from a single blast, then you can match them together on the software, which I'm going to demonstrate when I'm on the interface. Using the software underground, also we work in the underground mine. We also analyze material in the underground mine. All you need in the case of underground mine is to have a lighting setup, because the only limitation in the underground is lack of visibility. So if you can have two portable lights at the left and at the right, then you are good to go using image analysis technology in an underground mine. So I haven't mentioned this. I will be switching my screen to the interface of WhoopFrag software, which is an image analysis software developed for blasting assessment and quality control of blast material. So, but before I go, I switched my screen to the second part of this webinar. I would like to take question. If you have any question, feel free to raise up your hand or use the chat section of this meeting to share your question, or if you have any specific question about your mind, maybe you are going through one or two issues at your blasting section and you want to see how image analysis technology can help you, make decision and, make adjustment to your blasting. This is more than welcome. Yeah, if you have any question, feel free to unmute your mic also and share with us, or maybe you have an experience with image analysis technology, you've used it in your mind and you have a specific question, then I will be happy to answer your question. Okay, I can see someone typing at the chat box. I was gonna wait as I switch over my screen. Okay, you're joining another meeting. Yeah, thank you. Yeah, sure. The meeting is being recorded. All the attendees will definitely get a recording for the meeting. Okay.
It was very good, very interesting, very helpful for me. So I'm very, very sorry. I have
Okay. Yeah, no problem. As I've said.
keep contact.
Okay. Okay. Thank you. Yeah, so I'm going to be proceeding to showing the interface and also performing an analysis using the software. This is the interface of the software, easy to use software. These are example of analysis that I've done on the software. These analysis are projects in a limestone quarry to assess the material and make sure the quarry is blasting up to their expectation. And this is an example of projects going on right now and being presented. This project is focusing on reducing the oversized material in a granite aggregate quarry. So the first part of the project is being presented at the ISA conference this year, and the second part is currently being presented at the Frag Blast conference going on in Turkey. So, and to everyone attending the meeting, you're going to have access. I'm going to send a free copy of this technical paper to you. It's a technical paper that shows how you can perform a continuous improvement. It shows a framework of how to set up a continuous improvement for your blasting using image analysis technology as a checker. Here today, I'm going to be using an image from a limestone. So here I have this image taken with my mobile phone. So this is the auto scale feature of the software, and I'm going to also switch to in case you want to put a scale object. As I've mentioned, you can take the picture with your mobile phone in app. So if you take the picture with your mobile phone in app, the software is going to use an auto scale feature, which I've also attached a link. I'm going to send a link to a full version of how to take a picture with a mobile phone in app. If you take the picture with a mobile phone in app, you're going to have an auto scale incorporated with the image. Then what happens if you choose to change your mind, like, oh, I'm not taking the picture with a scale, I'm taking the picture by you want to put a scale object on the mock pile, then you can also do that. Here is an example. So the scale type that we have single scale, dual scale, then auto scale. Single scale in image analysis technology is when you have just a single object on that material as a scale reference. As you can see here, I have a ruler on this image as a scale reference. Then dual scale is when you have two scales, two objects on this image that you want to use as a scale reference. In this case, when do you use the dual scale? You use dual scale to correct for magnification error. For example, here I just want to cite an example of the importance of using dual scale in image analysis technology. I'm going to open my camera, and here I'm going to demonstrate the effect and how this can easily affect your analysis if you have any mock pile that is pyramid, that is a slopy material. Here is two light rod of the same length. They are of the same length. So when you are taking the picture of a material, since image analysis technology use reference to account for the size of each of the particle, so those material that is far away from you and is not at the same level will not appear to be the same size in the image. So in this case, this is the same rod. This rod is closer to the camera, as you can see here, and this rod, the other rod, is far away, making this rod to appear as if it's bigger than this one, because this is closer to you and they are at different angle. So this is slope. This is a slope. I create a slope between them by putting this at a far approach. If you have a border at the top of the image in a slope, and you have another material the same size of border closer to you, but because of the slope, the effect of magnification, this is appearing to be bigger than this border. So to account for this in image analysis technology, you use two scale reference. So the scale reference, one of the scale objects you put in on the mock pile will be at the top of the mock pile. Then another object, scale object, will be at the base closer to you. In this case, the software is going to account for any effect of magnification created by slope or distance variation. Then question always arises that what distance should I stand when I'm taking the picture? The first thing we give as a recommendation is that you stand at a distance where the biggest boulder in that image is only representing 20% of the image you are taking. I want to take that again. It's one of the rule of thumb that will give as recommendation. If you are taking a picture of a blast material, make sure you are standing at a distance where the biggest boulder, the biggest particle in that picture you are about to take only occupy 20% of the whole image area. So that is one of the rule of thumb. Then the other way you can know the distance to stand, if you are taking the picture in app, the rule of thumb is that any distance that you are standing, such that the frame, when you activate the in app uh, uh, picture taken in the software is going to show you a green grid line, like a green frame that you can use to make adjustments or make decision based on the distance. So any distance you are standing, such that the base of that green frame is aligning with the base of the material, the floor base of the material that you are taking the picture. So in today's webinar, I'm going to be using a single scale, which is this ruler on this material. And the first thing you need to do if you are using a single scale is to define the size of the scale. In this case, this is a 15.5 centimeter ruler. So here I mentioned the size of this object I have on the PAL. I define the unit I'm working with. You don't want to be working, you don't want to measure the size of this object, a known object, in meter, and be working with centimeter. So here I'm working with centimeter. So the next thing you need to do is to zoom in and identify edge to edge of that material. So you drag edge to edge. Now we've set our scale. You can log the scale. Then this is the first step, setting the scale. Now we've set the scale and we are good to go. Then what happens if the image are captured, like in this case, have external area that I don't want to include in my analysis? Then you can proceed to the editing, and there is a cropping tool on the software. It's called the area of interest. So you select the cropping tool. You can easily crop around the image here if you want to exclude some section of the blast. So sometimes we'll take the picture and we have like an excavator included, or there is the mine face included in that blast. So you want to crop that section. Then after the cropping, you proceed with the edge detection. Here I'm going to show you the differences between the two type of edge detection, which is the traditional approach and the AI driven approach. The traditional approach in WIPFRAG 4 is called the simple edge detection. So for the simple edge detection, you need to adjust this slider to account for the perfect particle edge detection. So if you have a particle edge detection of your interest, then you can proceed with the editing. As I've mentioned earlier, this approach requires long time editing. You need to edit the particles you have like a perfect, like kind of algorithm or edge that fits your interest. How do you know when you need to do editing when using image analytics? As I've said, this technology allows you to manually edit the analysis if the edges are not well defined. Let's take, for example, this is a particle here. After applying the edge detection at 45 percentage of the extension bar, I have this particle to be appearing here. This is a O particle here, but it's appearing as multiple. You can see this is called the disintegration error. When you double tap on the screen, you activate the heat map material characterization to see how many particles are in this image. So you can see here, this is when you slide down, you can the heat map is going to fade up. You can see this particle is not appearing as one, is being downsized by this particle detection algorithm. So in the traditional days, that is in the olden version, that is version 3 point and 2 point, you have access to manual editing tool, which you can easily use to edit this. One of the two is the tool number 5, which will allow you to redraw the net manually by yourself. So imagine redrawing this net manually for all these particles is going to take a long time before you can be done. So here we correct that error, which is the disintegration error. We are able to detect the particle. Doing this might sometimes you can see the editing time here. I just spent 9 seconds in this particle. You can spend longer time on this particle. And here is other information about the image that we have taken: the latitude, the longitude, the altitude, the angle of the camera that I used to take this, and where the image is taken from. So here is, then if you don't want to spend longer time on this analysis, then what is the way forward? Since blasters are, blasting engineering team, blasters or blasting engineer don't have the time to keep editing, then you go with the deep learning algorithm. With the deep learning algorithm here, you apply the net, you generate the net. The algorithm is going to clean up the mix and give you up to 80% or 90% perfect net. Here is the new net. You can see the particles have been cleaned up, and all those error that we have earlier in the previous algorithm has been corrected. Then you can, if you still need to do some editing, as I've said, using AI or using artificial intelligence approach to detect the edges of the particle will not deny the users the right to still do manual editing. AI is good, but sometimes AI might not be able to get the perfect edges of the particle. Then you can proceed to use using the manual editing again to still cross check what is going on. Is it okay? Do I need to do any editing? If you are done doing the editing, you can check here, right here as the user of the software. You can right click here to see the particle sizes. That is, you can see the 50 biggest particle in this material. As you can see, when you activate these two, it shows you the 50 up to 50 biggest particles and where they are located. If this is a blast that I designed, I know definitely something must be wrong. If I'm getting good fragmentation here, and right here at the left hand side of this bench, I'm having poor fragmentation. So this is a call to attention. What has happened to this blast? What happened to the design in this section? Why is the design in this section, if I'm using the same body and spacing, the same stemming, the same charge length, then what happened to the material here? Then it's a red flag to start tracking what is going on at that section of the mine. If you do the second blast and you access the image, the same thing is still happening in the same section of the bench, then is a call to attention. Maybe I need to investigate the rock strength. Sometimes the strength of the rock at that section might vary. It might be that there is an intrusion that have higher strength compared to this section. It could also be that there is blowout. Maybe you need to increase the stemming in this area. Maybe there is discontinuity, there is fracture. Then you can easily investigate the drilling operation to see the penetration rates during the drilling in order to track what is going on at this section. Then another thing you can do when you click these two the second time is that the two can help you assess the performance of your blast by comparing the whole of this material with the crusher that will be handling this material after the blast, or with maybe the loader. So what you need to do is to, for example, enter the size of the primary crusher, that is the crusher that will be handling this material. When you enter the primary crusher and you update this to the two is going to show you the material that is bigger than your primary crusher, that is counting the number of boulder that you need to reblast or use hydraulic breaker on. So if you enter the size of your crusher or maybe the size of your bucket, the excavator that will be loading this material, you can easily know which of this material will give the excavator problem. Because if this boulder is bigger than the bucket of this excavator, then the excavator is going to spend more time, or the loader is going to spend more time navigating around this material to pick it up and dump it into the bucket of the truck that will be transporting the material. So these two allow you to check the performance of the blast by counting the boulder. That is all about that too. Then you can click on the name of the image and edit. Maybe this is from bench 1 and maybe this is picture 1, for example. So you can edit the name of the picture here. That is, taking the picture, you edit the name of the picture. Then another thing that you can do, especially when you are blasting in a metallic ore, is use this software for dilution control. Dilution is when you have barren rock, waste rock, or unwanted material section included in the high graded zone. So in this case, reducing the cut off grade of the material that you've blasted. Most of the time we have intrusion in the iron ore or intrusion in the pyrite ore, then reducing the concentration of the material that we are blasting. So this software, using the image and difference in color of the material, can help you track the percentage of the material that have dilution. So in this webinar, I'm going to be assuming that all the section of this material in this picture with black spots is my high grade ore. For example, maybe this is my iron ore ore. So the iron grain content is concentrated where I have black color. The first thing you need to do is to select the color ID, then put your cursor on where you have the red dot, then drag the cursor. As you hold on the cursor, the software is going to identify the black spots in that on that rock. As I've said, in this case, we are assuming that the black spot is where we have high concentration of high grade ore. Then you set that. As you can see up here, the software is going to create a profile pocket for the grade of the material as a function of the color. If any section of this rock that is blackish, or maybe that is pinkish, or maybe that is bluish, is the section that is of high grade, then the software is going to create this pocket based on the intensity of the color. So we are done with this. Is high grade. Color ID 1 is high grade. Then color ID 2 will be the low grade or the waste material. If, for example, you have a dolomitic intrusion, maybe marble intruded material, or maybe you are blasting spodumene and you have material intruded as blackish. So in this case, we are assuming the whitish section. It could also be that the whitish section is the high grade. So the whitish section of this particle, we also want to highlight them. So you drag on them and you have the software scanning the material and identify any portion of the material with whitish. If you want to enrich, maybe this is not whitish, you can also remove some section. So the software will identify those sections by itself and create a pocket profile. Then you set to color ID. ID 1, we said every blackish spot on this particle is high grade. Then every whitish spot is low grade. Then we'll set the two color ID. We proceed to generate the particle size distribution curve. This software is self-developed kind of software in such a way that you can give a feedback if you're using the deep learning, and how is the quality of the deep learning. Do you still spend more time in the editing? Then if you spend more time, you can easily report like, oh yes, I use the deep learning, but the deep learning I still do some editing. Then what we get back as a feedback from the software is that picture, we're going to ask you, maybe you give the permission, we can use that picture to also train the next model. We release model like every quarter of the year. Then by the time you'll be using the software in the next 3 months, the model will have been improved and is going to do a better job on that kind of image. Here is the particle size distribution curve. As I've said, this curve is going to give you the chart, that is the report from the software, will give you information about the size distribution as an histogram, the size distribution as a curve, the size distribution in numerical order, and the size distribution as a summary. Talking about the summary, here on the summary box, we have 6 parameters. The first parameter here is the DAT. You can have other parameter included, but here we can only have 6 at once. The DAT is the size that stands for the 80% passing of this material. That is, in this material that we have analyzed, 80% of the material in this picture is smaller than 188.96 millimeter. Then the biggest boulder, that is the biggest particle, is denoted by the X max. That is the biggest boulder that this blast that generates from this blast is 254 millimeter. How do you use the X max? You use the X max to checkmate if you are using the right burden and spacing. You want to make sure that the X max that you are getting from this report is smaller than your spacing or your burden. So if you are getting an X max that is bigger than your burden and your spacing, that means the strength or the explosive energy, the wavelength that is generated from your explosive within the burden and the spacing is not sufficient enough to fracture the rock in between each hole. Then you want to adjust your burden or spacing. Then what happens if the X max, that is the biggest boulder in the blast, is significantly smaller than your burden and spacing? Is an assurance to let you know that you are generating too much energy, breaking the rock more than what you expect. Then you can expand your burden and spacing. In this case, when you expand or you increase your burden and spacing, you save more money on explosive energy. You save more money on drilling, because the number of holes you'll be drilling to occupy the same bench width will be reduced. Then the 75 is 75% passing, while the N is the uniformity index. The uniformity index is showing how uniform your materials are. If you have high uniformity, then you are breaking the rock into similar sizes. Then, as I've said in when I was generating showing the dilution control application of the software, I mentioned that we create the first color ID as the high graded material, that is material with blackish spots. In this case, we are saying the blackish spot is where we are having the high concentrated ore. Then the whitish ore is where we are having intrusion, that is low grade ore. In this case, in this image that we just analyzed, 49 percentage of the particle in that image is having high concentrated high grade ore, while 43 is having low concentrated high grade ore. This is the curve summary. So you have the histogram also showing the size class of the material, the percentage passing. The interpretation of this is that, for example, we have 66 percentage of 66 particle in that image in this blast that falls below that have a sphericity of 0.69. The sphericity in this case is the shape of the particle. So the software will help you to assess the shape, the size, and color of the material. So the shape denoted by the sphericity is the ratio of the length to the width of each of the particle. So when you have a sphericity of 1, for example, you have the material to be highly uniform, almost spherical. So here at the top, you can see a line distributing the sphericity of each of the particle. Here, you have a sphericity close to 1, that is the material in this class, that is 8 particle in this image have almost uniform size, that is they are almost spherical. Okay, so here is the particle size distribution curve. Then this is the sieve set, which you can easily adjust, is an adjustable sieve set to fit into your requirements. Maybe you are not interested in the material in this range from 100, or maybe material from uh 21 downward. You don't have any material in that range, you can easily delete them. Then if you have other size of interest, maybe I want to see material, maybe if I have a crusher of 400 millimeter, what will be the performance? You can easily include that size, and it says everything in this image will go through 400 millimeter sieve or crusher inlets. And as I've mentioned, you can include other summary here. You can only have a summary 6 particles parameters at once. So you have other parameters here like the X50, the D90. So you can include any of those parameters in this chart box. To export the report for this analysis, you can edit the report also. Maybe this is bench 1 from gold mine, for example. You can, or gold mine, or you can rename depending on what you want to include on the report. So this name will be included. Then when you right click on this chart, also you can also include other information, like including the scale object, then including the net. You want to see the heat map, then you want to see the color of the block. Then another thing that I like to mention here is that you can set a specification. For example, if this blasting is expected to go to a crusher of 1000 millimeter inlet, and you want to see if all the material, you can set your specification. For example, 80 percentage to 100 percentage of this material should be compatible with this crusher. Then you go to other size classes, for example like 250. Maybe you want to ensure that this material is meeting your specification. 75, for example, to 85 percentage of this material should be in this size class. Then if possible, is 0 to 5 percentage of the material should be in this size class. You can create an envelope. In this case, I've just created this envelope. You can also still fine tune the envelope, in this case to follow the chart and to meet your specification. In this case, I'm just going to say is 0 to 5, for example, at this level. So you can track this envelope to make sure that you keep checking any of the blasts that you are performing in this mine. Then if you want to also assess the blasting efficiency based on the crusher inlet, all you need to do is to enter the size of your primary crusher. For example, if your primary crusher in this case is 250 millimeter inlet, then the software will tell you the percentage of the material that fits in. That is, you have 98.96% of this material that can go to your primary crusher directly without any issue. Then if you want to also see how you're saving energy, maybe for example, you have a secondary crusher and the secondary crusher is 100 millimeter. You want to know the percentage of the material that can directly by cut. You don't need to send this material to the primary crusher. You can send it directly to the secondary crusher. You can access that also with this. Then if you we can set this envelope in such a way that the envelope fits into the curve of our demand. In this case, I can change the envelope like this and also make adjustments to this to make sure that the envelope fits into what I'm interested in. Here I set the envelope to be 80 to 90 in this case to make it looks more as we want it to look. So here you can see you can adjust this envelope depending on your expectation. Then exporting the result from this software, you can export as PDF, you can export as image, you can export as CSV, then you can export as ANA file. So let's see an example of an exported PDF from this image. You can save that to directly to your local disk, and here comes the report. Here is an example of the report in this case. So you can see the report will show the name of the mine, the full detail, then the characterization of the material with a legend that you can use to interpret the material. Having mentioned that, you can also apply calibration in case in situation where you have finds, that is, you want to account for the hidden finds. Calibration with either sieve analysis results or using empirical equation, flat calibration, that is using an adjustment with a flat calibration to account for hidden finds. You can also use a blast cast for continuous improvement if you want to adjust the blast parameters to to simulate the next blasting. So here when you apply the blast cast, you can adjust this parameter to make sure that you have, for example, you enter the parameter for this design. If this design is 1 by 1, for example, and you enter all these parameters, you can log this to account for the log factor. Then you apply that. When you set this parameter, you can easily maneuver, like what will happen if you increase your burden. For example, the blue curve is the current blast, the red curve is the simulated blast. So you see when I change the burden to 1.5, it means that changing the burden to 1.5 will increase the number of boulder that I'll be getting, and I will be getting more fines also because there will be a lot of blowouts in this design, and the blowout will be over crushing the blast cola drill hole cola section, creating more fines and creating more boulder. So this is a blast cast. You can always use the blast cast also. Then merging multiple images, you can combine multiple images. In this case, if I have 3 images from a single blast, I can click the 3 dots here and click this chart. Then I'm going to have 3 images merged together. Then I have this as a single image. Then you can also create a profile. You can create a project profile here. For example, let's say this is webinar picture, for example. Then all you need to do is to drag those images that you've analyzed. If this is the image, these 2 images, this is picture 1, picture 2 from a single blast. You can put them into a profile, or maybe you put them in the profile. Then when you click the profile, you have the 2 images meshed together. You can also view the 2 images as separate. Then you can see if there's any improvement or continuous, the blast 1, then the blast 2, comparing the 2 images together. A case study application of the software, as I've mentioned, is this. Here is a result from a continuous improvement study. This is a continuous improvement envelope. This is what we want the blasting curve to fall in within, and we've performed 6 blasts. At the first blast, we benchmark the current state of the blasting, that is this first curve. This is where the mine particle sizes are before we start the study. Then the first thing we do is to change the stemming material. We change the stemming material size, we increase the stemming material size to confine the blast energy, and we'll start having an improvement. Then after that, we increase the stemming length, and currently we are here, and we want to shift the curve such that the 80 percentage of the material that is being blasted can go directly to the crusher, because currently any material bigger than the crusher inlet is being handled by an hydraulic breaker in the mine. So this is an overview of what the image looks like for this continuous improvement study. As you can see in this example, this is the last blast from the study, and just opening that up to show you an example of UAV view of the image and how it looks like on the chart. So these are multiple images from drone image, drone fly. So you flew the drone on the blast, and several pictures taken, and you can analyze the image to see how the material is being distributed. So you can see this section, there is poor blasting at this section of the mine, and there is good blasting here. So here, this section is 1.8 meter stemming, and this section is 2 meter stemming. So there's a lot of poor confinement at this section, and there's a lot of good confinement at that other section. For the GIX, also, as I've mentioned, you can view the chart on the GIX on the software. Here, you can view the blasting right on site with the GIS application, and it will allow you to, see what is going on site based on the D80, the D90. You can see how the blast is being, the status of the blast right on mine. So here are the red dots, and the orange dot are those places where you have boulder. The hotter the color, the bigger the fragments, the cooler the color, the smaller the particle size. So here you can see different example of blast with drone images that I've analyzed as a study. Here, the section in this mine, this mine have a good fragmentation at the front row, but at the back row they are having a lot of poor fragmentation. And when we examine what is going on, there's poor confinement at the back, and it means that the free phase generated at this section of the blast is poor. So we're looking forward to adjusting the timing to control the movement of the material such that each row can give enough space for the budding movement to reduce the fragmentation in this state. Since we are having good fragmentation at the front row, but at the back there's poor fragmentation because of the delay timing is very poor. There's poor budding movement. Having mentioned other information about the systems that can analyze material on conveyor belts, I like to show an interface of an example of that system to show us how the system interface looks like when you taking the picture on belt, and when you doing the analysis with online system. Doing the analysis with online system means that you're taking the picture on moving conveyor belts, and as the conveyor belt is moving, you're taking the picture of the material in real time, and you are doing the analysis in real time. So I'm going to show an example of that here. So as I said, the WIFRAG software is serving as the HDMI interface to view the system. So this is an example of a demo picture system. Here, this is the moving conveyor belt. The camera is mounted on the belt, and as the material is moving on the belt, it's taking the picture and is doing the image particle size distribution in real time. So you can see what is going on the belt within time, like maybe in a week. You can choose to see what is going on in week, in month, in days. So you can decide what you want to see. For example, I want to see what the material looks like within from February 1st. For example, from February 1st, in this case, February 1st to April 1st, for example. So I just want to see what has passed through the bet within this time frame. So the system is going to merge all the pictures, hundreds of pictures that have been taken within the month, and it's going to give you a particle size distribution curve of the material, seeing the sizes and seeing the summary, and if it's missing your specification. So in this case, if the material is not meeting your specification, the system can communicate to you. It can send you a report through through your mobile phone or also through your control system on site. Thank you very much for your time listening to this presentation. So I would like to take your question. If you have any question, as I keep showing an interface of different what you can do with the system. If you have any question, I would like to, take your question. In this case, so this is still the interface of the solo C system, showing you as the material is moving on the bed, is taking the picture, is doing the analysis, and is also showing the report in real time. Yeah, so thank you very much, and really appreciate joining the meeting. Do you have any question? Yeah, then at this section, if you have any issue with your mind and you want to discuss that, you want to ask question how you can, which part of the, which feature of the software can help you solve that, yeah, you can also ask that. Also, I would like to share some other features, capability of the software to address specific needs. Yeah, then if for any reason you like to, have like a team, like another meeting with your blasting team, such that we can give another presentation to the team on how to use the software, feel free to send me a mail or reach out to me. I'll be more than happy to show you more feature of the software with your team members to let them see how the software or the system can be incorporated to your mine operation. Thank you once again for joining the meeting. I'm so happy to have everyone. And if you'd like to share, you can unmute your mic now and talk about maybe your name, then where you are joining from, and maybe the mine you're working with. Yeah, thank you. Okay, thank you everyone once again for joining. If you have any question, feel free to reach out to me. My email I will use my email to send a recording of this meeting to you. Feel free to reach out to me for one-on-one training with your blasting team, with your mine team, or you want a presentation for your mine uh, colleagues. Feel free to reach out. I'll be happy to set that up with you. Thank you very much. Thank you, Kristen. Where are you joining from, Kristen? Oh, Kristen is joining from Peru. Thank you very much for joining the webinar from Peru. I'm so happy to meet you. Let me know if you have any question after the meeting. Feel free to send me a mail. Yeah, the webinar. I'm currently in Canada. Yes, we're based in Ontario, North Bay, Canada. But we have a reseller in Peru. Okay. Okay, said, I have a question. In underground operation, where lighting and visible are often limited, how does whipware system identify? Oh, yes. The system comes with for the whipware system, for the system specifically, I just want to be clear. So for the system, the system comes with two lights. So it comes with two floodlights. So I just want to show an example of the installation on Beth. So this is a picture of the installation on Beth. So the system, let me try share my screen. So this is a picture of how the system is going to look like when you install it on bed. So the system is going to come with two LED lights. So the lighting system is going to regulate the underground lightning condition. So you have the system is going to come with the frame, is going to have these two floodlights, then the camera where you have the camera head taking the picture of the material, then the lights regulates the lighting condition in an underground mine. Then if you are taking the picture with mobile phone, like for the WebFrag software, yes, we recommend using two sets of lights. If you have two set of light, portable light, for example, this is an example of two portable lights. This is the stand, and this is how the light looks like in an underground mine. If you are interested in this kind of light, I can definitely send you a link to where to get this kind of lights. So this is what the lights looks like, and everything fits into this bus. So you can get this bus on Amazon. So I can send you the product name and everything. You can get that to set up a lighting in an underground mine. So all you need is just a portable light like this for image acquisition. You can use that to acquire image right on site. Then with the system comes with lightning system by itself. Yeah. Yes. Oh, yeah. Thank you, Kristen. Feel free to reach out to me if you need more clarification, or if you want me to send you a video on where I clearly explain how to set up a lightning system for image analysis in an underground mine. If you are considering WhoopFrag software, that is the software that you can have on your mobile phone or your PC, then you want to ask question on how to use this software underground. And I have a question coming here, like how can I get the software? How can I get the software, and how can I use the software? The software is available free to download, free to install. You can download on your mobile phone or your PC. Then you can use the software in three ways. Is either you download the software and you buy image credits. That is, you can use the software as you go. You buy a credit to analyze a single image, just in a low scale level, or you buy an annual subscription. With the annual subscription, you can have an unlimited analysis. Then it's offline capability. You don't need to be online. You don't need network. You can also use this a single subscription on 10 different devices. 10 different devices. That is, if you have a single subscription, you can share the username and password among your team, and every individual member of the team can use the software simultaneously. 10 different devices simultaneously. So it allows teamwork. So you can also use the service called the mail frag, where you take the image by yourself, then you send us the image, then you pay with image credits, then our technical specialists will analyze the image. You get the result within 48 hours. So when you click here, you can learn more on how to do that. You can buy this subscription directly online. Click in here, shop now, then you progress. You can buy it online. You can also message me and said, oh yeah, you need a quotation for the annual subscription. Then we'll be happy to send you a quotation for the subscription. Then if you are buying image credit, if you need a quotation, we only send quotation for image credit more than 100. Or you can also buy the image credits directly online. That is, I just need something to analyze just one picture for trial phase. So you can buy one image credits, then you can analyze one image on the software. Thank you very much once again for your time. And let me know if you have any question. Feel free to reach out to me. My mail, I've dropped my mail the uh, on the chat. If you're willing to mail me, if you have any question or you like us to have a professional training with your team. That is, you want to have your team being trained on how to use the software, or you need more information about the system, feel free to reach out to me. Send me a mail, say, Blessing, I need a quotation. Blessing, I need you to set up a training. We are having this issue in the mind. We like to use the image analysis technology to help us see what is going on in the mind. Can you train our personnel on how to use this and the approach we can set up to address this issue in the mind? Once again, thank you. I'll be happy to hear from you. Have a wonderful day. Bye.